Okay, guys, so here's the way this is going to go down. You have really kind of only one goal for today, but I think you're coming to appreciate that this intermolecular force stuff becomes so varied that within any particular concept, it can go 11 different directions. But guys, your goal for today is simply this. You need to be able to predict and explain why some things dissolve in other things while some things don't. And you need to be able to think through and talk about and explain this relative to all potential solute-solvent combinations. So guys, the way that this is going to go down is we're going to build into this. And we are going to talk, first of all, about some terms that you need to understand. Now, I'm going to give those to you. And then, guys, we're going to talk about this thermodynamically. We're going to talk about energy going into breaking bonds. We're going to talk about energy coming, not bonds, intermolecular forces, but energy going in as attractions break, energy coming out as attractions form. And we're going to understand this thermodynamically. But, guys, as long as I've been at this, I've never really seen this treated thermodynamically. The fundamental idea is it's going to be handled conceptually when they will ask you, why does this dissolve while this doesn't? And then it becomes a matter of understanding the underlying chemistry. So, guys, that's the way we're going to approach it. And that is then this. This is the double top secret decoder key that allows you to think through all of the possible solute-solvent interactions and not only why they dissolve, but how to talk about that. So guys, we have till 12:25, 11:25. Should be lots of time. Let's dig in. So guys, we're going to start with some terminology. Some of it's familiar, some of it's not. Here we go. So guys, when we talk about solutions, we're talking about two components, right? What are they? Solute and solvent. Do you need to write it down? I don't think so. So guys, solvent is the dissolver. The solute is the dissolvee, the thing that is being dissolved. Now, guys, we talk about this idea of major and minor components when we talk about liquid-liquid systems, but we'll talk more about that in a minute. It's not, you know what, I'm just going to get rid of it because you're going to find it distracting. There we go. Okay, so guys, for our purposes in here, what we're going to do is we are going to talk about liquid solvents, and then we're going to talk about solutes in all three phases. And then we're going to watch some really bad videos. Okay, so guys, terminology first goes like this. Terms you need to know relative to dissolving. The first one is solvation. Some of you are starting to tremble a little bit because you understand where this is headed. In order to really understand dissolving, what do we need to do as a group? Watch the dissolving video. Yeah, 12th time this year. I'm convinced that you could actually teach AP chemistry just by showing the salt dissolving in water video. So guys, what is solvation? Oh yeah, yeah, yeah. I remember my very first day in my very first chemistry class as an undergraduate. Dr. Anthony Guzzo was my Chem 105 professor. This really thick accent Italian guy. He looked like he was going to die at any moment. There's 400 kids in the class. He could barely get around. he used to tuck his hand in his pants, kind of like Napoleon, only more disturbing. And I remember him saying, kids, thick Italian accent that I'm not even going to try, the only difference between you and me with the PhD is I finally understand all the stuff that you're going to learn this year. Like, oh crap. But guys, really there's some truth to it. If you could watch the salt dissolving in water video and really understand everything that you were seeing, there's a lot of good chemistry there. So, solvation. Thought number 2, hydration. Hydration, guys, is simply solvation when the solvent is water. Term number 3, saturated solution. Too fast? Are you okay? So guys, if you've got a sponge and it is saturated, what can't it do anymore? Can't soak up any more stuff. Guys, same thing is true here. If you've got a solution that is saturated, it can't soak up, if you will, any more solvent. So guys, a saturated solution is a solution in which the addition of additional solute will not enter solution, but it will remain as a solid. So if you're making salt water, and if you're adding salt to the water, eventually you get to the point where it can't be any more salty. And the addition of extra salt will not dissolve. It simply falls to the bottom. That solution is understood to be what's called saturated. So guys, I know some of you will be interested by this, so let me actually give it to you, whether you choose to write it down or not. The technical definition, sort of drink deeply of this. The technical definition of a saturated solution is beautiful but simple. Ready? A saturated solution is a solution in contact with its solute. Isn't that cool? Why do you know that that's a saturated solution if the solution's in contact with its solute? What would happen if more could dissolve? The solute wouldn't be there. So if you've got a solution in contact with its solute, you know that it's saturated, because if it weren't saturated, that solute would dissolve. It's really, there's something just fundamentally kind of cool about that definition. Okay, so then guys, the next term that you need to know is solubility. The solubility is the amount of solute needed to form a saturated solution at any given temperature. And we'll talk about the temperature dependency in just a minute. Then guys, the last 2 terms that you need to know apply to solutions, if you will, where, for example, you're dissolving a liquid into a liquid. So ethanol, right, this stuff. This stuff dissolves in water. If it didn't, there wouldn't be bartenders. So guys, this stuff dissolves in water. But here's the trick. If I had a bucket of water and I started dumping ethanol into this, you couldn't add enough ethanol that eventually no more would dissolve. It would just continue to mix in equally. It would continue to dissolve indefinitely. So what if we had a cup of water in a bucket, a cup of water, and we dumped in gallons of ethanol? Well, initially, the ethanol would dissolve in the water, but then when there was more ethanol, we would think about it as the water dissolved in the ethanol. See what I'm saying? It never becomes saturated. This is a unique type of solution that you cannot saturate. Because you can't saturate it, we can't talk about solubility, because solubility is defined as the amount that's needed to saturate it. But if you can't saturate it, then soluble all of a sudden doesn't apply. So instead we use the word miscible. Miscible describes liquids that form solutions in all proportions. So technically, we don't say that alcohol is soluble in water. We say that alcohol is miscible in water. So what about oil? Does oil dissolve in water? It does not. But technically, instead of saying it's not dissoluble in water, we would say that it's immiscible. So guys, immiscible simply means liquids that don't dissolve significantly into each other. And of course, the example would be things like gasoline in water, oil in water, things like that. Yeah.
So I think maybe I've got like a wrong definition of dissolving, because when I think of putting water in ethanol, I just feel like they mix. Like, what's the difference between mixing and dissolving?
So depends on what you mean by mixing.
So I mean, like all of the for any given amount, for any given sample of that mixture, there will be an amount or a proportional amount of water.
So the important thing to think about though is as those, with dissolving, as that happens, it's those intermolecular forces holding the solute and the solvent together. Go ahead. And so when we picture, for example, salt dissolved in water, and we've seen the video 11 times, we've got the sodium ions surrounded by the water, we've got the chloride ions surrounded by the water. Eventually, if we add enough salt, there just isn't enough water to continue to surround the ions because they're all busy with other ions. Where in a liquid-liquid solution, they're sort of surrounding each other. So the water surrounds the alcohol, but the alcohol surrounds the water, and it doesn't really matter who's surrounding whom because it's all just mixing together, as you said. So when we think about these miscible mixtures, liquids in liquids, we don't think about one being the solute and the other being the solvent. They're just, as you said, mixing together. Is that okay? Yeah. Guys, go ahead.
What liquids are like a liquid mixture?
Uh-huh.
No,
so either they do or they don't, but they don't saturate. So, for example, alcohol dissolves in water. We say alcohol is miscible in water. Gasoline does not dissolve. If you've ever been out boating and you spill gas in the lake, it forms a film. Right. So water and gasoline don't mix. They don't dissolve. They are immiscible. So either they do or they don't, but they never saturate. Is that okay?
Yep.
We good? Correct. Yeah.
When you have the solid and liquid,
Mm-hmm.
you're going to have your liquid latching on to solid.
Exactly. Right. And because this doesn't start as a solid, we think of it differently. Yeah. So when you say it's two separate processes, you mean dissolving solids versus dissolving liquids in liquids. And you're right. Yep. So guys, let's take a look at this then and apply our new terms. Here it comes. I know. I'll mute it. So guys, it goes like so. We got the water molecules, they come in. All right. Oh, whoa. I know. Oh yeah. Can't get enough.
Maybe on lab next time we should do it. You should just watch this.
I know. Okay. So guys, what we need to do that we haven't done before. So, first of all, miscibility has nothing to do with this because this is not a liquid in a liquid, it's a solid in a liquid. But now let's talk, because guys, again, you could teach AP by showing this video. There's so much going on here. So, talk to me about that. What's going on there? That's hydrogen bonding. Hydrogen, we'll be careful. You could use hydrogen bonding on the test. They're fine. But we prefer to call those hydrogen forces. So guys, we've got an intermolecular force there. Talk to me about this. That's ionic bonding. Now let's talk about this dissolving process. So now guys, we've got attractive forces that are forming here. And what type of intermolecular forces are those? Those are ion dipole forces. Now, guys, let's talk about the terminology that we're going to use here. And so guys, what I want to do is I want to go away from this for a minute and then come back to it. But in going away, I want to take you over here because I think it's a better image of what we're talking about right here. So guys, now what we've got is a clear representation of the process that we call solvation. Remember the term that you learned, solvation is the surrounding of solute particles by solvent particles. But because these solvent particles are water, we don't just call it solvation, we call it hydration. Do you now understand how these terms apply to the process? Is that okay? Okay, so guys, with that done now, what I want to do is I want to foreshadow everything that you're going to learn today. Okay. So, stupid question. Does table salt dissolve in water? The question that you've got to be able to answer is why. You ready for the answer why? Guys, I'm going to actually, blue would be better. So guys, the reason that table salt dissolves in water is simply this. Because this is stronger than this and this added up. That's it. That's why salt dissolves in water. Let that sink in. Guys, the reason that salt dissolves in water is because this is stronger than this and this added together. Now guys, as we talk about this, now let's add some energetic thoughts to it. What's this up here in the upper left? Hydrogen forces. Now guys, in order for salt, let me say that differently. In order for water to dissolve salt, what has to happen to these hydrogen forces? They've got to break. Is that endo or exothermic? That is endothermic. Now guys, in order for the salt to dissolve in water, what has to happen to these forces right here? They also have to break, which is also endothermic. Now that we've got the water separated from the water and the salt separated from the salt, then we end up with these intermolecular forces, these forces of hydration. And again, what type of forces are these in this particular example? Ion dipole. And as these ion dipole, hold on Rebecca, as these ion dipole forces form, is that endo or exothermic? Exothermic. So now guys, let's go back to what I initially said. Why does table salt dissolve in water? Because this is bigger than the sum of this and that put together. What does that then mean these processes will be thermochemically? Exothermic. So guys, the idea is this. This is bigger than this and this put together. That's how we know when salts will dissolve. Energy has to go in to break the solvent apart. Energy has to go in to break the solute apart. Energy is released when the solute-solvent attractions become present. Just a minute. Now guys, as we think about this, let's tie that back to chapters 5 and 19. Guys, what types of, relative to endo and exothermic, what types of processes are spontaneous? Endo or exothermic? Exothermic. So all we're doing, guys, is reinforcing what we already understand, that exothermic processes tend to be spontaneous. But now, if you're in the lab, you remember that when you went in and did this lab, right? Remember the lab where you recorded all your data up on the board? Some of you found out that your salts were endothermic when they dissolved. And even if you're not in the lab, guys, you understand the quick cold pack, right? So guys, we've got this quick cold pack, and we know that this quick cold pack dissolves spontaneously, but it's endothermic. So guys, if this is endothermic, which one of these is greater? The thing on the right or the things on the left? The things on the left. So how did we explain that this could still be spontaneous if it's endothermic? An offsetting increase in entropy. You're starting to realize you need to study for the AP test at the end of the year. But guys, the big idea is this. When most salts dissolve, when most things dissolve in water, they are exothermic, meaning that this is greater than the sum of these. For the few that are endothermic, the reason that it still happens is because of an increase in entropy. But guys, for now, we are simply going to say that things dissolve when this on the right is greater than the sum of these, meaning the net process is exothermic. Just a second. Go ahead. Bigger in terms of energy. It gives off more energy than it takes in. Is that okay? Go ahead. Oh yeah, right, yeah, good, right? Because we're going, wait a second, we saw the lattice energy tables. Good night. We appreciate how strong these ionic bonds are, right? What does that now actually help you understand the strength of? These ion dipole forces. These ion dipole forces are stronger than the ionic bonds in the lattice. Yeah, the reason is because there's two things going on. There's a multiplication of force, because remember, it's not one water molecule that dissolves it. Going back here, it's not one water molecule, it's multiple water molecules. So we end up with a multiplication of force. But also understand this. Initially, some of that energy that goes into breaking down the salt is not the energy of attraction between the salt and the water. It's kinetic energy, because these water molecules are slamming around and they hit these salt ions and break them off.
So maybe I'm looking at this like flow chart. So maybe the ion dipole and the ion.
Yes, but exactly. Yeah, you got it. Go ahead, Matt. No, that's a good, and no, thank you. So, and Matt's right on this. It's not quite this sterile, right? Because even as you're saying, there would still even be some hydrogen forces there, right? It's not like salt dissolves and then the water boils with the salt in it, right? So, and that's a good point, that when we come back and we say that the hydrogen forces are breaking, they're not fully breaking. The ionic bonds are. The ionic bonds in the salt crystal have to completely disrupt or it can't dissolve. But the water is still in the neighborhood of other water molecules. So those hydrogen forces don't have to completely dissociate for the salt to dissolve, but they do weaken. Go ahead.
So is the trigger point, because something has to trigger all of these reactions, is the trigger point that kinetic energy of me just dumping water into that salt, or the salt?
It can be, but there's still attraction even without the kinetic energy of temperature or pouring. It's just not as efficient.
Okay.
So here's what you need to understand. Going back to our previous thought, and this is going to be horrible on that background, but the big thought that you need to understand, if these represent the breaking down of the forces in the solvent and the solute, and if this represents the creation of forces between the solute and solvent, this is bigger than those or it doesn't dissolve. With the few exceptions of the end, like the ammonium nitrate in water, but the big picture is that simple. Okay, you guys okay with that big picture? Okay, so guys, what I'd like to do then is I'd like to represent this for you in another way. Please don't write this down. Please don't write this down. Guys, here's what we've said. And understand, this is not stepwise. This is not step 1, step 2, step 3, but here's the way we're going to understand the dissolving process. It is 3 processes happening simultaneously. Guys, process number 1 is the breaking apart of the solute particles. In the example of salt water, what type of forces are these? Solute, oh, did I touch? Crap. Don't touch the board. Okay, so guys, what are the forces inside the solute in salt water? Ionic bonds, right? Okay, what are the forces between the solvent particles? Hydrogen forces. What are the what forces are being formed between the solute and the solvent? Ion dipole forces. So guys, and as we said, these two are endothermic because they're being separated. This one is exothermic because it's forming. And then guys, we kind of write an equation. And I know when you see equations, you're thinking we're going to do math. You're not going to do this math. But guys, what we are saying is this. These two are endothermic. This is exothermic. So we can at least say this. If something's going to dissolve, which is bigger? The two on the left or the one on the right? The one on the right. This is bigger. And if nothing else, we can say then that delta H is negative for this to dissolve. And that allows us to go back and talk about the idea that spontaneous processes are exothermic. See what we're saying? You're not going to have to do the math, but it's worth tying to the math because it helps you connect this back to what you learned in chapter 5. So guys, with that said, what I'd really like to do is show this to you graphically. So here's what we're saying. Process number 1, separate the solute. Process number 2, separate the solvent. Although, as Matt pointed out, not completely. Process number 3, let them reorganize. And guys, the energy diagram for that actually looks like this. Do you see it? So guys, let me show you what we're saying. We're going to go blue. Okay. Oh, why did that do that? Come on. So guys, it goes like this. So the idea then is if here we have the solute and the solvent. First thing we've got to do is break down the solute, then we've got to break down the solvent, then the interactions form, and we end up with the solution forming. Notice that here the solution has less energy than the things that make it up, so this would be an exothermic process that would dissolve. Now guys, here, when these separate, this would be an endothermic process because the net solution has more energy. Now, will this dissolve? Maybe. If what is true, if we're creating lots of entropy. So if this system creates lots of entropy, it will dissolve. The systems on the left will always dissolve because it's net exothermic. The system on the right could dissolve if there's a high enough corresponding change in entropy. We're just going to leave it at that. So we're not going to dig deeper. You just need to be satisfied with this. Are we digging deeper or being satisfied? Okay, sounds good. All right. So guys, with that said then, we now need to use this to figure out when things will and will not dissolve. So guys, grab the table that I gave you and let's talk. Okay. Oh, there we go. So guys, you're going to want to write into this table with me. So now that we understand the processes that have got to take place in order for something to dissolve, guys, you got to conceptualize it like this. We've got forces inside the solute, forces inside the solvent, and forces between the solute and solvent. You with me to there? Okay, so guys, with that said, let's do this. We're going to go red. Okay, so guys, we are going to talk, well, let's first of all help you understand how this is organized. So guys, on the left, we've got solvents. Across the top, we've got solutes. And this all relates to polarity. So, what does polarity have to do with this? Well, if something is polar, what do you know about the strengths of its intermolecular forces? Weak or strong? Strong, right? Therefore, are they easy or hard to break? Hard to break. So guys, with that in mind, let's do this. Thinking solute. So guys, let's talk about polar solutes. I gave you the most polar of solutes, which would be salt. It's so polar, it's ionic. So what do you know about the forces of attraction inside of salt? Weak or strong? They're strong. Let's write that down. So now guys, what do you know about the forces of attraction inside of oil? They're weak, right? Those are nonpolar molecules. These are weak intermolecular forces. So now guys, let's look at solvents. Water. Strong or weak intermolecular forces is a polar solvent? Strong. Now guys, what about down here with nonpolar like gasoline? Weak. That's why gasoline evaporates so readily. Okay, so now guys, we're going to work our way around this table. Here's your goal, to figure out why these things do and don't dissolve into each other. So looking in the upper left-hand quadrant, here's what we know. The solute-solute interactions are strong. You see what I'm saying? So we've got salt. These have got what are those strong forces? Ionic bonds. So guys, what about the solvent-solvent interactions? They are also strong. The hydrogen forces inside of water. You guys may want to write that down. Ionic bond, hydrogen force, just so you know what you're talking about. So now guys, here's the question. What about when you get them together? When you take salt ions and water molecules and mix them together, what will be true of the solute-solvent interactions? They are really strong, and this is what Rebecca was talking about. We get that multiplication of forces. These are really stinking strong, and that dissolves. Do you get the idea? Okay, now guys, let's do this. Let's move to the right. So now we're going to talk about oil dissolving in water. Does oil dissolve in water? No. Let's figure out why not. You ready? Let's look at our stuff. So now our solute is oil. What do we know about the attractive forces inside of oil? It's weak. It's actually induced dipoles. Oil molecules are these long, enormous, nonpolar blobs of carbon and hydrogen. But they're so big and polarizable that their induced dipoles are strong enough to hold them together as a liquid. What about the forces of attraction inside the solvent? Well, that's still water. Those are hydrogen forces. They are crazy strong. But now, guys, what about this? What will be true of the attraction between the polar oil and the the polar water and the nonpolar oil molecules? Super weak. Guys, think about it this way. These polar water molecules have got nothing to grab a hold of. The oil molecules over here are going like this, and the water molecules got nothing to grab a hold of because its poles aren't even stationary, right? You've got these instantaneous dipoles. The water's got nothing to grab a hold of. So guys, these solute-solvent interactions are very weak. Now guys, check this out. As a result, this can't break down this. The water is more attracted to itself than it is attracted to the oil molecules, and consequently, that doesn't dissolve. You get it? So now, guys, let's go down bottom left. And let's look at our characters. First of all, solute. So guys, our solute now is salt. Very strong ionic bonds. What about our solvent? Well, now our solvent's gasoline. Again, nonpolar molecules. What are the intermolecular forces in gasoline? Induced dipoles. They are very weak. So now, guys, what about this? What about the forces of attraction? Well, maybe we should say this. Does salt dissolve in gasoline? It doesn't. Let's talk about why. So, guys, what do we know about the salt? Really strong ionic bonds. What do we know about the gasoline? Induced dipoles. Not much going on. And guys, the induced dipoles in the gasoline certainly can't induce dipoles in the water or in the salt. And even if they do, they're moving around so fast and sloshing back and forth that there is virtually no attraction. So the solute-solvent interactions are very weak, and this does not dissolve. So now, guys, let's go bottom right. It's kind of sad. So now we're looking at oil and gas. Does gasoline dissolve in oil? Or does oil dissolve in gasoline? Either way, it's miscible. Do they dissolve? Yeah. Let's talk about why. Well, what about the forces within the solute, the oil, induced dipoles? What about the forces within the solvent? Very weak, induced dipoles. So now what about the forces of attraction between the solute and the solvent? They're also weak. But they are a little bit stronger because we get that multiplying effect. So guys, it's kind of like this. These guys both have weak attractions to one another. So because oil is not attracted to oil and gas isn't attracted to gas very well, they may as well just get together and hook up with each other. It doesn't take much to break, seriously, you know people like this. They have no friends, so they may as well date, right? Sorry. So the idea here, guys, it's really true. Their attractions are so weak that, guys, it doesn't take much to get them together, and consequently they dissolve. Now, guys, here's the thing you got to understand. There is an amazing analogy that I could give you about how all of this works, and it's a social commentary about why cheerleaders date football players. And I typically share all of this, but I know you guys can't handle it. So I'm kind of ashamed of myself that I mentioned they may as well date because they don't have any friends, because sure enough, you heard it, and all of a sudden, you guys are going everywhere. Come back. So guys, let's talk, because you need to be able to summarize this. But guys, understand, the summary is only for your purposes. You will never write this summary on a test. But let's look, guys. Let's look at the combinations that dissolve here and here. So let's look at the combinations. The combinations that dissolve are polar to polar and nonpolar to nonpolar. There's a way that gets summarized, and it's on your paper. And the way that it gets summarized is like dissolves like. Polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. But guys, understand, you never get to say that on a test. You can use it as a guiding principle. But when you start to explain it, you've got to come down, you've got to come over here, and you've got to talk about their relative attractions. So why does like dissolve like? Well, it's here and it's here. And that's what you've got to talk about. You can't say like dissolve. You can't say sugar dissolves in water because like dissolves like. You don't get to do that. Okay, so guys, wrapping up today then, let's do this. What determines how much stuff will dissolve in water? Well, first of all, pressure. And guys, I'm not going to give you time to take notes on this. We're just going to talk about it. So the idea is this. Actually, let's do it this way. You just need to understand it. So guys, this is the deal with pressure. So here we've got a beaker of water. And if we put salt in the water, changing the pressure does not change the amount of salt that dissolves. So the solubility of solids and liquids is not pressure dependent. If you were to put this in a bottle and pump it up, no more salt would dissolve. But guys, what if you were to seal this starting over, what if you were to do this, seal it, got some water, and then you put some oxygen in here, and then you increase the pressure? Will more oxygen dissolve in the water? Well, let's even do this. Let's make our gas carbon dioxide, and then we can think about this. So guys, if you've got carbon dioxide under pressure, more of it will dissolve in the water. Can you even picture the carbon dioxide under pressure getting driven into the solution? So guys, how do you know this is true? Because you know that when you screw the lid off of a Coke, all the carbon dioxide comes out of solution and it goes everywhere, right? That's why your Coke blows up when you screw the lid off, because you've got all this carbon dioxide dissolved in the water, and it stays dissolved when the pressure is high. But when you screw the lid off, the pressure goes down, the carbon dioxide comes out of solution, and it just bubbles up everywhere. You get the idea? So guys, finally, let's talk about temperature and solubility. And guys, it goes like this. I'll show you the picture, and then I'll show you something neat if we've got, I think we'll have time. So guys, what about temperature and solubility? And guys, it goes like this. It's sort of interesting, and you may want to go back and review this. But talking about things dissolving in liquids, this one over here represents solids. So as the temperature goes up, this is a measure of solubility, the number of grams of salt that will dissolve in water. So what happens to the solubility as you increase the temperature? Solubility increases. Why? The water molecules are moving faster. They're less attracted to each other. It allows them to grab a hold of the salt and carry more into solution. But guys, look at what happens here. When you increase the temperature on a liquid, this is now the solubility of gases in water. And what happens to the solubility? Goes down. Why would that be true? Well, now everything's moving more rapidly, and those gases jump out of solution and they go up into the gas phase. Guys, this is why it doesn't make any sense to fish in the middle of the day on a hot summer day. Because on a hot summer day, the water heats up. What happens to the amount of oxygen dissolved in the water? Goes down, and the fish are suffocating. And then in the evening, the water cools, more air dissolves into the water, more oxygen in the water. They can breathe more easily, and they can run around and eat, hopefully, whatever you're throwing at them. But guys, that's the idea behind this. Does that make sense? Yeah? Yeah. Uh-huh. I'd rather. You just need to know that the solubility of solids goes up. Okay, so now, guys, I want to show you something neat. Where? Oh, yeah, no, there's a 2 there. It just didn't copy right. That's H2O. Guys, let me show you this as a way to wrap up today. I want to show you about something called supersaturated solutions. These are pretty cool. So the idea goes like this. Let's take, for example, a salt like, do you really want to stay? All right, this will take 2 minutes. So guys, potassium, any of these salts, as the temperature goes up, the solubility goes up. Well, guys, you can actually trick these solutions to do something pretty cool. What you can do is you can heat up the water and you can dissolve a bunch of salt in there. Then, if you allow the water to cool slowly, so like at 90 degrees, you can get about 55 grams of potassium chloride to dissolve. Cool it down to room temperature, it should only be 25 grams. But if you cool it slowly enough, those extra 30 grams of potassium chloride will stay dissolved in the water, even though they shouldn't be there. And then if you drop in 1 crystal of potassium chloride, now all of a sudden the extra salt that shouldn't be dissolved there has a place to go, and it all crashes out of solution. It's called a supersaturated solution. Let me show you the video. So guys, this is how supersaturated solutions behave. So here's, actually, let me show you the other one. This one's better. So this is a supersaturated sodium acetate solution. They dissolved about 200 grams of sodium acetate into this water at boiling and then cooled it down to room temperature. There's about 5 times more sodium acetate dissolved in this water than should be. Guys, watch what happens when you add a crystal, and I'll show you it coming in. It's right there. There's the crystal of sodium acetate that they dropped in, and watch what happens. All of that extra sodium acetate crashes out of solution, and it goes down to the amount of sodium acetate. And it's funny, you take these things and then turn them over, and they don't pour. They've just basically solidified. It's pretty cool. All right, so guys, with all of that said, here's your homework. We'll see you Wednesday. Have a good day.